We're starting early? Should I wait? To start? Okay, I'll just start then. Hi, everyone. It's a pleasure to be here. It's been a while since I've given a millimeter wave related talk, so I'm really excited to be back to the band I love dearly. A little bit about me. So I was Dave and John's grad student when they were back in Chicago. Currently, I'm wrapping up my postdoc with Suleymanzade's group, where we're working on some quantum networking experiments with solid-state defects in nanophotonics mostly. And I will be starting my own group at Berkeley in about 2 months. So that should be fun. Okay, so my talk is going to be a little bit weird in a sense that we're going to go first dive into like one of the main millimeter wave projects, and then I'll try to zoom out a little bit and describe why am I still excited about this band in the context of the science that I would like to explore in my own group. I changed the title of my talk slightly last minute to millimeter wave photons for hybrid quantum systems, because in fact, that was the title of my thesis, which is for an AMO person is a very strange thesis title. And I still kind of consider myself a cold atoms person. But this millimeter wave band during my PhD has become a little bit of an obsession, as you can see from these random devices that I got to play with, and most of them were actually kind of side projects that I got distracted to. But thankfully, John and Dave were supportive enough for me to explore. But the main project that I did, and which was kind of how I started in the millimeter wave band, was transduction. So the idea was very simple. We really like optical photons, and then we have atoms which can interface with optical photons and ions and whatnot. And of course, there are all these amazing microwave-mediated platforms, and specifically superconducting circuits. So during my PhD, I built this hybrid system which combined optical photons in optical cavity, microwave or millimeter wave photons in superconducting millimeter wave cavity. And since Maxwell equations are linear, so photons don't usually talk to each other, we needed some sort of a mediator. And in our case, we, as atomic physicists, we decided to put in atoms with Rydberg excitations. So the idea is kind of simple, and again, the motivation is very much bringing together the platforms that we love, that especially recently both superconducting circuits and, for example, neutral atom arrays have been developing at really high rates. So it will be really exciting to be able to bring them together with some of these experiments. Right, on the superconducting circuits, we really like our strong photon-matter interactions, really fast control. On cold atoms, we have long coherence times. The fact that every atom is the same, it's really nice for scalability. And now with these new tools of tweezer reprogrammability, there's really nice connectivity and parallel performance. And of course, the optical interface, which is kind of why we used atoms for transduction in this particular project. And the reason, so Dave, in his talk, said that he wasn't quite sure why we did millimeter wave, or it might have not been very well motivated, but I remember quite well is that the reason we wanted to go to millimeter wave photons, because we really, really did not want to put atoms in a dough fridge, because we thought it would be very hard, and I think it was true to this day, but kind of one of the main motivations was like, well, can we do some sort of proof of principle experiment on transduction with atoms without having to go full-on ballistic with dilution refrigerator? And just to kind of give you a flavor, of course, like after the previous talk, I'm really glad the background was kind of laid out, but atomic systems usually require a lot of lasers, a lot of optical manipulation that requires some cooling power. At room temperature, we kind of take it for granted, because at room temperature, the cooling power is kind of infinite. In a fridge, you have whatever cooling power at that stage you have. So it's really hard to budget thermally for these atomic systems in the fridge. So motivated by our desire not to go to Dill fridge, we kind of decided to push it to higher frequencies. And then what was really nice, that there were kind of a couple of things that ended up working in our favor. So for example, yes, we want to go to higher temperature and still be able to resolve single photons. That means we need to go, let's say, to 100 gigahertz. But that also means that if I'm going to be interfacing microwaves with Rydberg atoms, I don't have to go as high in N, in the Rydberg state, on the Rydberg side, which is also really nice because the polarizability of Rydberg atoms goes with like N to the 7. So that gets really painful, as was discussed, once you bring atoms in Rydberg state close to surfaces. So that was kind of nice. You get like a one nice desire, you want to go warmer, more cooling power, and kind of for free, you're giving a little less sensitivity to surfaces. So, okay, so atomic transduction has been a motivation for a long time. There have been a lot of experimental attempts and then a lot of theoretical proposals. I haven't put all of the transduction efforts ongoing on chip because both Mark and Amir and many others have laid out such wonderful kind of intros to transduction done in other platforms. So I just wanted to present some of the atomic attempts, and these are not all of them. So our kind of transduction approach is the following. What's the following? So we use rubidium-85 atoms. Specific species choice is really not important. We picked rubidium because it's an easy atom. We picked 85 because it's more abundant as an isotope. So and the idea is very simple. You have 780 nanometer optical photon, which is your optical transition in the transducer that kind of excites an excitation in an ensemble of atoms to the first excited state. Then you turn on the blue beam, and that kind of gets you to the Rydberg manifold. And then between the Rydberg transitions, you place your microwave cavity. In our case, it's a millimeter wave cavity at 100 gigahertz. And kind of to make sure that you have like a unitary operation, that the energy is conserved, and like you're not kind of once you trace out the system, you're not left with some decoherences because now you have like a mixed state with an atomic state. You kind of need to finish this loop with a UV beam that brings you back to the ground state. So that's our transduction loop. This is for the experts, it's a forward mixing. For us, it's kind of, you have the optical transition, you have the microwave transition, and you use two classical fields at blue and UV light to kind of close the energy conservation. And of course, transduction is always really about impedance matching. That's when you get the highest efficiency. So the idea is like now that you have the system as a mediator of transduction, you need to find a point at which it can efficiently transduce information from optical to microwave and vice versa. So just to kind of reintroduce cooperativity, which has been also done many times at this workshop. So on the optical cavity QED system, just to give you a flavor of numbers, usually we're talking about the cooperativities of around 100. And you can kind of play around. You can increase G a little, but sometimes you also have to increase kappa a little. So it's very hard to really, in optical, purely optical regime, to get significantly like orders and orders of magnitude higher than 100. People are really pushing it to 1,000 and 10,000, but it's kind of, this is, the 100 is a state of the art that has been achieved now in multiple systems. And of course, this is a very experienced superconducting circuits community. So you guys obviously have a dramatically stronger light matter interaction, so cooperativities could be much, much higher, which is a really interesting and kind of a nice feature of circuit QT. Okay, so for our transducer, just to kind of give you an intuitive picture, we kind of can think about 3 steps in a transduction, kind of the optical, the classical blue that gets you to the Rydberg state, and then the cooperativity of the millimeter wave emission. And then you can describe the internal transduction efficiency as some combination of these 3 cooperativities. But again, at the end of the day, it's really about a kind of an impedance matching problem. Okay, so the idea is very simple. Atoms have the microwave transition, atoms have the optical transition. We know how to kind of transfer energy from one to another. Well, how do you actually build the system? So it looks very clean and in the cartoon. In the actual life, it's kind of a monster of an experiment. So this was still at U Chicago. This is kind of the start of my PhD. This is the end of my PhD. And then it was shipped to Stanford afterwards. And now it's even nicer and bigger. So that's very exciting. The experimental, like a heart of the experimental system is this hybrid cavity. And in fact, a lot of our efforts was spent to really figure out how do you put mediators and at the intersection of optical and microwave cavity and be able to do the transduction without kind of ruining the properties of each resonator and still be able to manipulate atoms. So the superconducting cavity is niobium. It's our kind of favorite material for 3D cavities at 100 gigahertz. I will mention exactly the kind of specificity of this superconducting cavity, but Dave kind of already mentioned, like at the heart of it is really 2 drilled holes or 3 drilled holes, as many as you want. But the idea is that you take 2 or 3 or n evanescent tubes at specific frequency, and the intersection of these evanescent tubes creates a mod volume that's bigger in cross-section than each evanescent tube itself. So you can trap light at the intersection of tubes, basically by just drilling holes. So these cavities were just drilling holes. So that was kind of the insight, one of the insight of my PhD. And the nice thing about this kind of types of cavities, so the reason I kind of went into this direction is that, again, we were inspired, of course, by Hiroshi's work, where you could get these like really, really long coherence times, really long lifetimes. But of course, you sacrifice the G because the mod volume is really large. We all know that, when you have kind of big volume with respect to surfaces, you can get really high Qs, but you're sacrificing speed of your interactions. So we wanted to kind of go into the opposite direction. We want to be able to somewhat still preserve the cooperativities, maybe not as high as these previous works in larger cavities, but we want to get into a regime where you can kind of increase the G without too much sacrificing the cooperativity. So we wanted a small mod volume. So one way, of course, is to go on chip, but that sounded hard. So we decided that why don't we try to decrease the mod volume as much as we can in 3D, knowing that we probably can get higher Qs and a little bit less painful experiment. And a kind of intersection of these tubes is the best I could come up with during my PhD. And the nice thing is the diameter of these tubes is about a millimeter and a half. You can, just have 2 intersecting ones. You can have 4. You can have it kind of in a circle. In fact, you can drill multiple in the array and create like grids of cavities. And these are really, really tiny kind of cavities, like millimeter scale. So that was really exciting. And of course, the thing that we needed was not just a cavity. We had some kind of parameters were required from it. We wanted low mod volume, as I mentioned. We want high quality factor because we want to preserve the coherence of the microwave photons as long as possible. This is the tricky one. We really needed optical access to the atoms because the atoms would be inside of this microwave cavity, and that's kind of hard. We wanted optical access for laser beams to manipulate the light, the atoms, and we all wanted integration with an optical cavity. And this is why kind of this tube approach ended up being really nice, because one of the tubes is basically the axis of your Faber Pro. We literally just put a mirror here and a mirror here. Yeah, that's your optical cavity, and it's kind of auto-aligned to your millimeter wave cavity. And because these two tubes are still relatively large for the beam sizes, you can shine laser beams through the rest of the holes. So it kind of really worked out really nicely. It was kind of a cavity designed for a specific need. And after kind of learning all these tools of making nice cavities with etching and HF and all that kind of stuff, we're able to get 10 to the 7 Qs at 1 kilo. So that was really exciting. We weren't sure at that moment that we'll be able to make high Q cavities with low mode volume at 100 gigahertz. So that was exciting. So because we're integrating it with an optical cavity, we also want like a vibration isolation. So my lab mate during PhD figured out this really nice way of like not using a glue to attach mirrors to the cavity. So we ended up with like more or less stable configuration of like a hybrid superconducting optical cavity. And in addition, because we don't use glue, it's more robust to thermal cycling. So the cavity doesn't break as often after like 2 or 3 thermal cyclones, which had happened with the previous designs. Okay, so this is what the system looked like. This is kind of a janky 2-chamber setup that the folks right now have to work with. Apologies. So I was building it as a G1, but basically it's a 2-chamber system. One side is basically where the pulse tube goes, and there's a cold arm reaching into very much AMO-looking chamber with windows and atomic sources. We use a grating mott to be able to just kind of shine one beam inside of the system and trap atoms. And this is what the inside of the chamber looks like. So for superconducting circuits, it doesn't look that crazy. For AMO folks, it looks pretty crazy. Usually the inside of the chambers are much cleaner and nicer. So we have some charcoal over there, which is pretty odd again. But charcoal, by the way, is a really nice way of getting rid of reflections because it really like absorbs and diffuses the optical light really nicely. So without it, you can't see the mott. The moment you put charcoal at the back, your pressure goes down and you get really nice imaging. So I'm a big fan of charcoal. So yeah, so this is what the inside of the system at least looked like when I was still a student. This is the cavity. So that's the mott right here. And then about like 7 centimeters or so below the mott volume, you have this little hybrid cavity. So the idea, I like making cartoons, you trap your atoms using a grating mott, then you put it in the optical conveyor belt, you lower it down into the hybrid cavity, and here your atoms can now interact with the optical photons, and if you excite them to the Rydberg state, they can interact with the microwave photons in kind of the same spot. So that was the goal, and then that's kind of what we achieved. I jumped really straight into the results because I want to get to other stuff as well, but kind of to see that we're coupling to the millimeter wave cavity, first we kind of, well, we like to think about polaritons in atom cavity world. So you can think about it as just like a combined excitation of a photon and an atom. So we call it a dark polariton because it's like narrower. And so you can see by like detuning the atomic transition to the microwave cavity, even without any microwave photons inside, you can see, you know, when you're in resonance, your dark polariton is much lossier. When you detune it from the cavity, it couples much less, so it decays less fast. So this was kind of like an indication of we're coupling to the resonator mode. So that was exciting. And then finally, we did the full transduction experiment where this is kind of transduction efficiency. This is internal transduction efficiency. I personally get a little confused when people give efficiency numbers. I always have to like figure out, is it internal? Is it the total? It's exciting that now more and more the papers that come out, they start citing total conversion efficiency. I think it's an ultimate kind of like a sign that the field is moving forward. So this is internal conversion efficiency of about 58%, but it's not too bad. The total efficiency was about 2%, and well, 2.5%. And just perfectly frankly, this was not like really optimized to have a really high efficiency of transduction. So there's no really a good reason it should be 2.5%. So we think with some upgrades, the internal conversion efficiency could be above 95%, and then these impedance matching on the microwave and optical side could get dramatically better because these are kind of beefy, big systems. Yes? Oh, yes. So this is basically, yeah, that's a good question. So basically, this is the impedance matching. So kind of, if you had just one cavity system, you could imagine, like, you know, if you have G square over kappa gamma, what you want is G square over gamma to be equal to kappa. So you kind of exchange energy as fast as you decay. This is your optimal. It's a little bit harder to think about it when you have like multiple steps, but kind of impedance matching feeling is very much the same. And so we get about 58% efficiency, bandwidth about a few hundred kilohertz, and then the noise photon a level below 1 at 100 gigahertz. And we were actually at 5 Kelvin at the time. So this was really exciting. And then just to show that we can kind of feel the statistics, at least between thermal photons and classical fields. We did not have a transmon to give us a single photon Fock state. That would have been also really fun. But at the time, we didn't have it. So basically, what we could do is to see what's the G2 look like for when we're not populating the microwave cavity ourselves. So there's some thermal population, and you can see the G2 at 0 is 2, which is what you expect. And then when you increase the microwave population, the millimeter wave population of the cavity, you can see kind of the statistic getting closer and closer to 1, which is again what you expect. So we were really excited about this. It's kind of like a highlight of my PhD, like this major project, but it really kind of got me to thinking, okay, so I was getting towards the graduation, I was thinking about what to do for a postdoc, and I did transduction, which when you're doing the PhD, you're kind of trying to get a system to work, but eventually you kind of think about like the context of your work, or like hopefully you get to think about it during your PhD as well. And since transduction is kind of meant to be a tool to interconnect systems over a network, so you have these amazing superconducting circuit systems, and unfortunately they don't natively have optical interface, but with transduction you can kind of bridge that. But it's not the only way to interconnect systems over the network. And that's kind of why I did what I did for my postdoc. So I wanted to kind of decide to try a different direction. So instead of thinking, okay, I have a network, I have superconducting circuits, which are like these amazing nodes of quantum compute, and I want to be able to interconnect them over distances that are, at the very least, they're outside of the fridge. So that kind of forces you to go optical. But the other way is, well, you can build systems from scratch that can have some compute locally, but and they somewhat natively have efficient optical interfaces. And there are many different platforms kind of working on this direction. There's NVs, SIVs, which is the work that I'm doing in my postdoc. IONS have been doing this for a while because if I understand this correctly, at some point, kind of the motivation was that this would be a path to scaling to a large number of qubits, at least like for part of the community. Neutral atoms are more of a recent phenomena, so that's really exciting to see more and more different platforms incorporating neutral atoms in different types of cavities. John is doing really awesome work here as well, but there's like many other types of cavities being built for that kind of efficient light matter interaction. So now we would like to zoom out a little bit. So this is a little bit odd. I usually start with a zoomed out picture and then we go narrow. But because it's a millimeter wave workshop, I wanted to kind of start with a transduction. And I want to talk a little bit more about quantum networks. So we kind of been talking about interconnecting systems and how millimeter waves could be put in this context. But I wanted to talk a little bit why we're building quantum networks. So what they are, it's this kind of distributed, you can think about it as a many-body system with classical and quantum channels between the nodes. So the nodes could be anywhere. Honestly, it could be tens of microns away in the same chamber, across two chambers in the same room, or it could be across countries. So kind of the idea is a simple. But what's important is that we're really thinking about interconnecting them with quantum channels as well. So you're able to put in, to send and receive wave functions instead of just zeros and ones. So that's kind of important. We usually think about optical interlinks for quantum channels because we're hoping that we're able to apply this over long distances. So just to kind of give you a flavor of information transfer, if you're trying to send quantum information via optical photons, let's say telecom, this is our favorite band, you will lose your like half of your photons within 10 kilometers. If you send the same information via, let's say, your favorite 780 nanometer light for rubidium, you will lose half of your photons in 100 meters in a fiber. If you try to do it with microwaves, well, if you take like a very much average RF cable, well, you have like 5 meters to go, but also the problem is that you can't escape the fridge because otherwise you'll be drowning in black body radiation. And this is really nicely described by him today. Okay, so optical channels are important. The quantum channels are important, and the optical interface is very important. So eventually we want to be able to send information, receive information in classical and quantum domains. We want to be able to distribute entanglement, and we want to use this distributed entanglement as a resource. So what kind of things we could do with this resource? So there's applications in quantum technology. You know, that when you think about quantum networks, probably the oldest and most famous applications are like quantum secure communications, so it's like QKD, and there's been a lot more since then on kind of like quantum communicational flavor. But for me, I really get excited about more large-scale compute kind of distributed applications. So for example, one of them is using connectivity, distributed entanglement, to basically increase the Hilbert space of your computation. So you can imagine you only have, let's say, 100 qubits, someone else has another 100, and the algorithm you want to run is exactly like 200 logical qubits somehow. So this is kind of like futuristic look at it. The other really exciting one is kind of combination of the secure quantum communication and distributed quantum computing. So this is so-called delegated blind quantum computing. So this is kind of like an interesting feature of distributed entanglement, where you could imagine I generate light-matter entanglement, which is kind of a building block for your distributed matter-matter entanglement. I keep my matter qubit as a server, and I send the photon down the fiber. You can hook up to the fiber, and imagine I encoded my photonic qubits in polarization basis. You can put in a wave plate, and then a polarizing beam splitter and 2 photodetectors. So you can basically rotate your wave plate in arbitrary directions and observe which photodetector fires. By that, what you're basically doing is you're measuring the photonic qubit on a particular basis. And what that does is that because you had a bell pair with my matter qubit that I'm still holding, you're steering my matter qubit remotely. The one nice feature about this is you're the only person who knows the basis of the measurement, and the only person who knows the outcome of the measurement, which means every time I try to measure my qubit, I end up with a mixed state. So I can't really know what you did. So it's a kind of like a little intuition for you how you can use distributed entanglement to kind of blindly run algorithms remotely on matter qubits that you don't know. So these are kind of applications in technology. I also get really excited about possibilities of these distributed systems for big science. And I mean big in a sense of size and scale. So you can imagine using quantum channels to distribute entanglement between atomic clocks. Aside from knowing time better, like a global time, more precisely, because you can increase the sensitivity by square root n, where n is number of bell pairs you can distribute between the clocks. You can also use this network as a sensor network that can now be kind of a probe of fundamental physics, like cosmology, gravitation, or searches for axions and whatever your favorite missing particles are. And then the other direction is also kind of interesting, is this like long baseline telescope ideas, where the idea was that, well, we're getting a lot of these amazing images from the sky, for example, this ring of a black hole, which was collected by an array of millimeter wave telescopes. But usually kind of, and the idea is like you do kind of interferometric measurements. So farther and farther where you put your telescope, higher resolution on the sky of the spot you get. But the problem is eventually, if the signal on the sky gets weaker and weaker, and the distance, but you still want to get higher and higher resolution, in order to directly interfere the signal, for example, if it's optical, you have to traverse longer distances. And if the photons kind of die on the way to the beam splitter, you're kind of ending up with a lot of noise. So you have a sensitivity limit to your long baseline. So the ideas with that by Gottesman and colleagues is that, well, you could distribute entanglement, and you can measure like in a sense f1 minus f2 or f1 plus f2, where f's are frequencies, without getting shot by noise twice. All right. Okay, so that's good. Yeah, so the idea would be to kind of distribute entanglement between telescope nodes and be able to kind of beat the sensitivity limit at really low signals coming from the sky. So it's a very blue sky idea, but kind of the capabilities for all of these, both quantum technology ideas and big science ideas, is that you need to have some compute locally, some computational qubits, some memory qubits to store information, and you need to be able to distribute entanglement at high rate. So these kind of ideas really excite me. And recently in Nish's group, in collaboration with Marco, on these beautiful systems on chip. So this is diamond nanophotonics that you see, kind of these Toblerone shaped nanobeam cavities. We implant silicon ions inside, then we kind of stabilize it in this silicon vacancy defect. And each silicon vacancy defects come with like 2 qubits for us, 1 electron spin and 1 nuclear spin. And we use electron spin as a communication qubit and the nuclear spin as a memory qubit. So it's a really remarkable cavity QED setup, because you can see we're like deep in bad cavity regime, which means we can send photons and distribute entanglement at a really high rate. So for an AMO person, this is a really remarkable parameter regime for cavity QED systems. So we've done some really fun stuff recently. We've established a 2-node kind of a network node where we can show photon matter entanglement, both with a communication qubit and with a memory qubit. We recently demonstrated matter-matter entanglement across our labs, which are located in different floors of the same building. We also showed distribution of entanglement across 40-kilometer deployed fiber in Boston area by going to telecom transition. And we're also able to distribute entanglement and hold our bell pair for over a second because our nuclear spin will live for so long. We've used this now entanglement to do some of these like blind gates. So we've shown like a universal set of blind gates from single to qubit distributed or local. So that was really fun. And then currently we're working on some of these alone baseline telescope ideas. Okay, so oh, okay, amazing. All right, so I get really excited about this kind of stuff, which you can tell. The one thing that always came to mind during this work we're doing, which is very exciting in this optical domain, is that how nice would it be to have more computational power? Like how great would it be not to just have 1 or 2 qubits? We can actually make like the tools that Marco developed in Diamond, we can make hundreds of cavities in Diamond. So that's amazing. And we can do photon-mediated gates on chip in principle. So we could have n qubits on each chip, where n could be relatively high. Unfortunately, if you want to do cavity-cavity, kind of like a qubit-qubit entanglement via photon, you kind of need to leave the cavity, come back to the cavity. So every time you get hit by all of these inefficiencies of like impedance matching and losses. So in some sense, it's kind of funny because distributed entanglement versus local entanglement has exactly the same process. So it would be nice if you also have access to multiple qubits that are coupled to the same cavity, where you can do n-qubit entanglement, and you can do some sort of like compute locally. So that kind of brings me to what I'm excited for in the future, which is in very much my personal opinion, kind of a new frontier, which is hybrid quantum nodes. So the idea is that, well, maybe there's something in between building transduction as an interface for systems that already exist, and building small systems from scratch, 1 qubit at a time. And the idea is, for me as an AMO person, mostly, what I'm excited about is kind of interfacing atoms, both with photonics and with superconducting circuits. And in context of this workshop, I will talk mostly about the superconducting circuits part. The idea is that these hybrid systems with optical interfaces can provide more computational power per node for like interesting encodings, information compression, even for like sensing protocols. It can give you more, kind of many more quantum channels, both in the optical and millimeter wave domains, which could be interesting if you're trying to, for example, sense weak signals in the millimeter wave. And also kind of give your system not only different types of channels, but also more of them, just because you have access to larger Hilbert space in the system. And then, of course, the goal is just more entanglement. And of course, the challenge here is complexity, and it's not something to do. So why I think millimeter wave are interesting for these hybrid nodes, some of these newer kind of generation. Well, of course, many of them have been already mentioned, and I only I'm mentioning subset of these ideas that I personally find really exciting for these hybrid platforms that have open interface. So one of them is operation at higher temperatures. Yes, of course, you can also use it for superconducting circuits and kind of increase the scale and operation. But if you're trying to push these hybrid systems, you also would like to have more kind of thermal budget for your system, because hybrid systems require a lot of cooling. There's a lot of interesting emitters. I've mentioned Rydberg atoms already, but there's more. Molecules have really nice rotational and vibrational states in this band. Also, both for kind of sensing the signals from them, but also utilizing them in hybrid systems. Spin defects, in fact, like for example, SIV itself has a 50 gigahertz and 150 gigahertz transition. And then the final thing really about the hybrid part of millimeter waves, which is I'm kind of motivated from my PhD experience, is that because millimeter wave band is kind of so intermediary, You can use both near field and far field tools. The other kind of, all of these four things kind of describe the same idea, is that, you know, you can use microwave engineering, you can also use array optics in the same band. You can use machining and nanofabrication, or you can do 2D and 3D without having to kind of explode in size. Of course, it's the fact that you're in an intermediate regime allows you to have access to both of these tool sets. It also kind of makes it suboptimal in both, just to be perfectly frank, right? So like microwave engineering is not as good in 100 gigahertz as it is in microwave, and similarly for array optics. Okay, so just to give you kind of a flavor, these are kind of emitters I'm excited about. So Rydberg transitions I mentioned. The molecules, for example, calcium fluoride has like almost infinite time in these transitions. And in fact, it's kind of interesting because for Rydberg states, higher you go in N, smaller the wavelengths become, or like energy, sorry, becomes smaller and smaller, where for molecules it's the opposite. So they get bigger and bigger. For solid state defects, again, these kind of transitions, some of these transitions depend on your B field that you turn on. Higher the B field, bigger the splitting. But some of these spin orbit couplings, they kind of come with a spin orbit and strain in the diamond. Although these are quadrupole transitions, just to be perfectly frank. And then finally, I just wanted to mention about these devices. So just to showing you a few that I've played with, to show you the diversity of different directions you can go. You know, you can kind of play with photonic crystals. These are like hard to say, but what these are coaxial cavities, your favorite ones with like a pin in the middle. So you've also machined those. They're fine. They're not easy at 100 gigahertz, but you can do it. This is a mirror that we machined in basically in CNC, like aluminum. We put two together and you could see Fabry-Perot modes. That was nice. So that's like paraxial regime for you. And of course, they've covered the 2D the cavities and these seamless cavities that ended up being quite convenient for hybrid systems. I want to kind of quickly note on the photonic crystal. So this is kind of ideas borrowed from more kind of optics side. So the idea was, you know, what if you can like reverse instead of having a field trapped in a dielectric, but what if you can have a kind of photonic crystal out of superconductor, but in reverse? This is not a novel idea. People use it in kind of different context as a metasurface or as a cavity, but it was really interesting. I wanted to explore how you can kind of make photonic crystals at 100 gigahertz, both using machining. This is like machined in CNS by me, in CNC by me, and this is nanofabricated by me at the same time. So it's kind of the scales are the same, but it kind of shows you that you can make the same device using two very different tools at 100 gigahertz. So for this, for example, what I wanted to see is like, okay, imagine I want to couple my seamless cavity with the holes to a sapphire chip with some device on it, let's say a transmon. So then I would want to be able to kind of put the sapphire chip close to your cavity mode. It's very hard to put a kind of chip inside of these holes because then like kind of becomes a coaxial cable and the light just leaks out of it. But you can imagine putting it like really close here, but then your cavity has to be very shallow, so it's very lossy. But what if you can kind of create a lid with a photonic crystal and suppress the leakage? And it's hard to suppress leakage at higher frequency, which is kind of normal. But I wanted to see, like, could you make a kind of a sneaky lid with a photonic crystal? And turns out you can. You can see, for example, I've played with a couple of versions, kind of see, okay, like without the lid, what is the Q? So it's around like 10 to the 4, which is like a very leaky cavity. You put the lid with a photonic crystal, and then you can go all the way to 10 to the 6, 10 to the 7 Qs. And I wanted to make sure that this is not just like a lid issue and not like actual photonic crystal. We also measured it kind of with a lid, but without photonic crystal. And you see that it is still very leaky because again, it's very hard to suppress leakage out of the kind of gaps at 100 gigahertz. So this was kind of nice. So this was made as a leakage preventer and kind of a packaging idea of like being able to contain a sapphire chip inside that's coupled to a 3D cavity. But on 2D, it could also be used as a resonate. And like this is kind of the idea. This is very much the view of the future. This is not like a real device, but it would be nice to be able to kind of replace a little sapphire chip with one of these Josephson junctions, similar to what Dave is working on, and be able to couple your really high Q microwave mode to this Josephson junction. Of course, from my previous work and in lab with John Simon, the idea is that you could, in principle, load atoms into the mode of this cavity as we did before. Okay. Another kind of direction, because these cavities are small, you can make, in some sense, like these skyscrapers of cavities. You can either couple them to superconducting circuits, or you can load your favorite atoms or molecules or whatever emitters you like. And then, it looks ginormous, but it's actually like this small. So it's kind of nice. And the way you make it is you take a block and you just drill holes, drill one hole this way, and then you have a bunch of coupled cavities. So the length scale is really interesting, because you can really play with some of these ideas of 2D, 3D, or quasi 2D at the length scales that are not super prohibitive for the fridge size. In principle, everything is kind of scale invariant because of Maxwell equations. Of course, the fridge is not scale invariant. There's very much a boundary to the fridge. So these things become kind of important. Okay, well, with that, I wanted to finish. So the lab is coming up in a couple of months. So we're really excited to explore some of these ideas with open quantum systems, and open not in terms of dissipation, but open in terms of being able to kind of interchange quantum information with large computers. And what kind of interesting physics and what kind of interesting quantum technology you can build using these platforms. So maybe we can even do some entanglement across the campuses. So that would be really fun. I've heard there is a fiber somewhere, so that could be interesting. Some of the things that I didn't mention, and this is more on the optical side, I'm also really interested in kind of creating and generating more entanglement out of atomic systems on the room temperature. So with by coupling to nanophotonics, kind of more, again, motivated from some of the work that Marco is doing on solid state defects, and with microcavities as well. So like these small cavities in the array configuration. As always, in my usual spirit, here's kind of like an animation of some of the fun stuff you can do with these like zoned architecture, photonics, microcavities, and single trapped atoms. And with that, I'd like to thank my postdoc group and Misha, and a wonderful group, which is like super fun to work with. Of course, Dave and John, who've been amazing PIs for my PhD, and really excited to have them in the area for the future. They can't get rid of me, it seems. And with that, thank you so much for your attention.
Yeah, very interesting works. So can you compare the pros and cons between the photonic crystal cavity for millimeter wave and the more regular, the cage-like cavities?
And sorry,
just the regular cavity design,
like a box?
Block, yeah,
or,
a box. Yeah.
Oh, I see. Okay, so yeah. So to be frank, so I did a lot of, so this is like years ago. We should probably publish it at some point. But it's my fault. I'm just delaying. So for this one, we didn't really create like a resonance structure with photonic crystal. I just wanted to see, can I suppress the leakage? And it was like exciting to see that you can. So these guys actually do have resonances, but these were made so suboptimally. Like in terms of like, I know for sure. So the Qs I got were like up to like 5×10 to the 4, like closer to 10 to the 5. But I'm very much sure that the most of the leakage is to the sides, like just like a bad engineering and not losses yet. So these were basically deep silicon etch and coated evaporated niobium, so very simple fab. And just kind of got distracted from this and went in a different direction. But I think you can do definitely much better. I do think for boxes, you can make nice box cavities, maybe like with the indium seal, like Michelle had like really nice papers early on. I think those could be applied for high frequency devices as well. I do think seams are actually a big problem for 100 gigahertz, right? Like higher frequency you go, the seams become more and more annoying. So this is what's kind of a motivation to see, like, does this help? And it was really nice to see, because like the size of these features, like under millimeters, and they were machined and then etched. So to have high Q. And it was fine. So as long as you don't hold it too long, because like at some point they disappear, the pins. But as long as you like etch them for a reasonable amount of time, you can get really nice low lossy circuits.
So this application to astronomy is very nice, but can you explain the role of the nuclei? Because you will have very long T1, but what about T2?
Yeah, so the T2s we have are also like seconds. So the T2 star is few hundreds of milliseconds, and with decoupling sequences we can get to 2 seconds. We've seen it like more recently in 2 seconds.
Will that be enough?
Yeah, so our kind of thought is that because we've kind of demonstrated that we can create entanglement between the nuclei and we can hold it for a second. Second seems to be like a good enough. It depends. If your signal is very infrequent, you can just generate more and kind of stack. So the idea would be you generate multiple bell pairs and you kind of wait. The thing that really actually limits you first is distance over which you're generating entanglements. So for us, we're doing it in a serial way. So the photon kind of comes into the first node, entangles with the nucleus and travels to the second node. So basically, if the distance is 40 kilometers, that's about like 250 microseconds. So your T2 has to be longer than that. And it's significantly longer. So the baseline can't be like 100 kilometers, but with our T2, without repeaters, it could be up to a few tens of kilometers.
But with repeaters, you could do.
You could, yes, yeah. I'm just thinking more of like if repeaters don't exist for a while, I think you could still do some of these interesting interferometric experiments.
Any further questions? Yes.
Excellent talk. Thank you so much. Learned a lot. My question is not very scientific, but what do you guys use to test these things at 100 gigahertz? I mean, is this like $1 million fridge, $1 million network analyzer?
It was
Or
not $1 million at the time. John can correct me. Did you guys buy anything for $1 million? No. So like when I was testing it, basically,
I mean,
it was
are they
like
cheap
VNA.
options?
There were a few tens of thousands, like up converters, like multiplied by 6.
Okay. So these are diodes, right?
Yeah.
Yeah. Okay. All
It
right.
was 40K.
Well, it depends if you include the PNX.
Oh, no. Okay. Sorry. That's a fair point. I did not include PNX. Just the diodes, there are a few tens of K. Yeah, that's fair. They're a bit annoying, though. Like Dave mentioned this, like there's a forest of sidebands. It's so upsetting. Very hard to do.
Okay. Is there any more questions? Now let's thank the speaker again.